Good afternoon. I am Dr. Nagla Mohamed from Computer Science and Engineering Department, Yanbu Industrial College. My work is queued combined guard channel and mobile assisted handoff call admission in 5G networks. Okay, so in the 5G networks carry different types of traffic such as voice, data, video, a lot of things nowadays. We have you can connect to the internet using your mobile. You can a lot of things. So these traffic types each have different quality of service requirements. So we require call admission control techniques to ensure that each traffic type achieves its required quality of service. Basically, call admission control is concerned with sharing the resources, because we have limited resources, we have limited channels. So different types of calls, for example, voice will require different bandwidths than maybe data, maybe video. So we need to share these resources. We cannot allow one type of call to monopolize the network. So that's why call admission control is required. Okay. Another thing that appears in wireless networks, we have something called handoff. So what is handoff? Handoff is when you are using your mobile and you're talking, or maybe you're using the internet, and you move from one cell to another cell. So when you move from one cell to another cell, you should be handed off to the other cell. So if there are no enough resources in the new cell that you're going to, then your call will be dropped. That is not desirable. In wireless, that is not desirable. It's not desirable to drop a call after it has been accepted. So that's why wireless call admission control have to prioritize handoff calls. Handoff calls, they have to be the priority of wireless call admission control. Okay, there are different strategies for doing that, for prioritizing handoff calls. One of them is called the threshold technique. In the threshold technique, we limit the number of new calls. The number of new calls will be given limited bandwidth. The rest, the handoff, they will be given, all the bandwidths will be available to handoff calls. Another technique is called the guard or reverse channel call admission control. In the guard channel, in the guard or reserve channel, we reserve a certain amount of bandwidth, certain percentage of the bandwidth for handoff calls. So if a handoff call does not find any resources available, it can take from the guard channels. Okay. Another technique is queuing. You can queue handoff calls until a free channel becomes available, and then they can be served. Another thing that we want to talk about here is handoff techniques. How is handoff handled? We have three types of handoff techniques. One of them is network control. The network is the one who controls the handoff. So, for example, I am using my mobile and I'm walking in the network. I am roaming around. Then when I move from one cell to another cell, the network is responsible for controlling the handoff. So the network is responsible for measuring for deciding when the call will be handed off to another cell. Another way is mobile assisted. In mobile assisted, the mobile will help in taking the decision. So my mobile will send message, it's the amount of powers that it's receiving from the base station, and then it will send periodically, it will send messages saying that this is the amount of power that I'm receiving, this is the amount of, so then the decision will be taken about to hand off or not. The decision will be taken by the network. The last technique is called the mobile control. In the mobile control, handoff is controlled mainly by the mobile. So the mobile will control the handoff mainly. So it's responsible for measuring the amount of power that is receiving from the base station. If the amount of power that is received from the base station drops below a certain level, then it will request from the network that I want to be handed off to another base station. So these are the three types. In this work, we are going to talk about guard channels plus, mobile assisted handoff plus guard channel CSE strategy. So we are combining two techniques together, because it has been discovered that the guard channel CSE strategy by itself is not effective. Why? Because sometimes a call will be given bandwidth, but later it will be discovered that its power is weak. The power is weak. So in this case, it will be dropped. So you have already allocated bandwidth for this call, but because of its low power, it has been dropped. So you are losing. Another also the Mahote or the mobile assisted handoff, also it has a problem, because sometimes the call will have a strong power and it will be accepted by the network, but when it goes when it's accepted, there is no enough bandwidth. So a better way is to combine the two strategies together, and in this case it's called the M+G CSE strategy. So Maho plus guard CSE strategy. What is the contribution of this paper? The contribution of this paper, we are modifying the Maho plus guard CSE strategy by adding a queue for handoff calls. This will improve the work of, because remember, we said that in mobile CSE, we are concerned more about handoff. We don't want to have so many handoffs to be dropped. So if we don't want many handoffs to be dropped, if we have a queue for the handoff, then that will improve the performance for handoff. Okay. Another thing that we do, mathematical analysis of the queued M+G CSE strategy for two customer types. We are going to have two customer types, N, which is narrowband, and W, which is wideband. Okay, so N will basically represent voice calls, and W will represent maybe video or whatever. The performance evaluation of the queued M+G strategy for two traffic types is conducted. So the system model that we're going to work on, we're going to consider one wireless cell. We're not going to consider two or only one wireless cell with a total of M channels. The M channels, they can be frequency channels, they can be time slots, or they can be in CDMA, they can be interference. It's open, okay? Arrivals to the system are from two customer streams. We have the N type, which is require one channel for their service, narrowband. W type, wideband, require VW greater than one channels for their service. Arrival process for type I is Poisson, with mean mu I, calls per unit time. Holding time of type I customers exponentially distributed with with mean mu I and unit time. Handoff calls for type I customers also form a Poisson process with mean rate alpha I. The cell residence time is the amount of time during which a mobile user of type I stays in a cell. Okay, it's also exponential distributed with mean theta I. The queue dwell time, maximum time that the call can spend in the queue before being dropped. So the queue has a dwell time. So a call cannot spend more than this maximum time, which is exponentially distributed with mean beta -1. The queue, then we're going to discuss, we're describing the queued M+G with handoff call CSE strategy. The total number of channels are divided into active channels A and guard channels B. Active channels can be accessed by all type of calls. So new calls or handoff calls can access the active channels. Okay, but the guard channels can only be accessed by the handoff calls. So active channels accessed by everybody, guard channels accessed only by the they can only serve the handoff calls. A newly arriving call is served from the A channels. If a new call arrives and there are no enough A channels to serve it, it is blocked. Okay. When a hard call arrives, then if it has an acceptable signal quantity, it will be served from the quality. It will be served from the A channels. Okay. What does acceptable signal quality means? We have in the network, we have a threshold for the signal power. If the signal power drops below this threshold, then we assume that the call does not have an acceptable signal quality. So if it has an acceptable signal quality, it will be served from the A channels. If there are not enough A channels for its service, then we get the extra channels from the GAR channels. Okay. If it's not, if the signal quality is not acceptable, then it will be dropped. Sorry, this is wrong. This is not accepted. This is wrong. If at the end of queue dwell time, not enough channels are available, the hand call is dropped. Okay, so the call will be if they are not sorry, here it shouldn't be not acceptable signal quality. It should be not enough channels for its service, then it will be queued. If at the end of the queue dwell time, not enough channels available, the call is dropped. Okay. This is the what did I do? I went wrong. Okay, this is the two-dimensional Markov chain representation of the system. Okay, so here you can see these are N calls. These are the N calls. These are the W calls. So we have if a call is accepted, it will go. If a call arrives with lambda I or with lambda N plus alpha lambda plus alpha plus gamma alpha N, it will go into one. The system will go into one W call. If otherwise, of course, it will stay in it. Okay. So this is the gamma is the probability that the system has acceptable handoff signal with good quality. Okay, after, of course, we did mathematical analysis. I'm not showing the mathematical analysis here. It's in the paper. We have here the results. A wireless cell is considered. We are considering a cell that has 30 channels. As we said, these 30 channels can be frequency, time slots, whatever. GAR channels are 10 channels. The queue size is 10. The N type calls need one channel. The W calls need 6 channels. The arrival, whatever, all of this. The probability of accepting a weak signal is 0.5. Gamma is 0.5. So this means a weak signal has a probability of 0.5 of being served. So it's a probability here. It's not because we cannot decide if okay. So this is the result that we got, the blocking probability of originating new type calls. So you can see this is the handoff calls, not queued. This is the one that has a star, the one that has a circle. Handoff calls are queued. So you can see there is a little bit of reduction for the queued ones. Okay. For the W type calls, we have they are basically the same. They are identical results, not so much difference. Here we can see the difference. Here for the calls that are not queued, the blocking probability is high. For the ones that are queued, it's reduced. You can see here it's reduced. It's less. Okay, and this is what we wanted because our aim is to reduce the handoff call dropping. This is for N type, of course. For W type, you can see the result here is much more dramatic. You can see here it's for the queued ones, it's much less than the not queued one. This is the average bandwidth utilization. So you can see there is an improvement in the a small improvement in the average bandwidth utilization or average channel utilization, so the channels are used more. In this figure, we are showing when we're increasing the queue size. So we started with a queue size of 5, then we changed the queue size to 10, the queue size to 15, the queue size to 20. So we can see there is a reduction. There is a reduction. Okay, so for the handoff call, for the N-type handoff call dropping, it's reducing with the increase in the queue size. So increasing the queue size led to a reduction in the handoff call dropping. For the W-type also, you can see there is a reduction. For the queue size 5, queue size 10, queue size 15, queue size 20. In the average bandwidth utilization, you can see there is an improvement. When the queue size was 5, the average utilization was low. Then here it started increasing until a queue size of 20. Of course, this is expected as the calls, they will not be dropped. They will be waiting in the queue. Okay, so in the discussion, there is no noticeable difference between the queued and non-queued for the new calls. Okay, why that is? Why? Because queuing is only for the handoff calls. So there is no noticeable difference between the queued and non-queued for the new calls. For the N-type, we noticed that there was a slight difference. For the N-type, there was a slight reduction, but for the P-type, there was no noticeable difference. This is expected as queuing is only for the handoff calls. Reduction in the probability of handoff call dropping for the two call types when there is a queuing. So for the handoff call dropping, there is a reduction. For the W-type handoff call dropping, reduction is much more than the case of N-type handoff call dropping. Why? Because N-type it requires only one call. So it's monopolizing the network. So when we use the queue, we give a chance, a better chance for the W-type, because N-type, they were using the network a lot. So now W-type, they have a chance because they can wait in the queue and they can get a chance. Bandwidth utilization is also increased when using the proposed strategy, expected since calls are waiting in the queue, and whenever a channel becomes free, a call is immediately served from the queue. Okay. Figure 7 to 9 depict the difference improvement of all performance measures when the queue size increases. Finally, conclusion, queuing of handoff calls in the M+G strategy led to reduction in the handoff call dropping of both customer types. Blocking probability of new calls was not affected. Average bandwidth utilization was increased. Okay. This is the end of my presentation. If you have any question.